Welcome to this video on advanced level physics, specifically focusing on Unit 1, waves and sound. A wave is defined as a vibration or disturbance in space. Sound waves require a medium, which is the substance they travel through, such as air or water. The first type of wave is longitudinal. In this wave, a fixed point moves parallel to the wave motion. Key areas are compression, where density and pressure are high, and rarefaction, where they are low. The second type is the transverse wave. Here, a fixed point moves perpendicular to the wave motion. Wave parts include the crest, trough, wavelength, amplitude, frequency, and period. Wave speed is calculated by multiplying the wave's wavelength in meters by its frequency in cycles per second. This gives the speed in meters per second. Here is an example problem. We can calculate the frequency and velocity using the given values, and then determine the wavelength. The calculated wavelength is 0.0319 meters per second. A standing wave is formed when a traveling wave reflects back on itself. The main parts are antinodes, areas of maximum amplitude, and nodes, areas of zero amplitude. Sound waves are standing waves caused by resonance. Resonance occurs when a forced vibration matches an object's natural frequency, resulting in vibration, sound, or damage. An example is shattering a glass with a specific musical note. Producing continuous sound requires setting up a standing wave pattern. Instruments are grouped into stringed, percussion, and wind, which are based on open or closed air columns. The speed of sound is influenced by density and temperature. In closed pipes, you have an antinode at one end and a node at the other. The smallest length of pipe to hear sound occurs when the length equals a quarter of a wavelength. This is the fundamental frequency, or first harmonic. Harmonics are multiples of the fundamental frequency. In a closed pipe, a node is at the second harmonic position, meaning no sound is produced at this frequency. Conversely, an antinode at the third harmonic position in a closed pipe produces sound. Therefore, sound in closed pipes is only produced at odd harmonics. Open pipes have an antinode on both ends. The smallest length to hear a sound is when the pipe length equals half of a wavelength. Since harmonics are multiples of the fundamental, the second harmonic of an open pipe will be one full wavelength. This is also called the first overtone. Adding another half wavelength still produces an antinode on both ends. Therefore, sounds in open pipes are produced at all harmonics. Let's work through an example. Given the speed of sound in air is 340 meters per second, we determine the fundamental frequency of an open-end air column with a length of 67.5 centimeters. Using the formula, we find the frequency to be 251.85 Hz. In this example, we calculate the lowest resonant frequency for a closed pipe at 37 degrees Celsius. First, we find the speed of sound, which is 353.2 meters per second, and then calculate the frequency as 57.90 Hz. Now, we will explore the concept of sound and the Doppler effect. Here is a question to consider. In general, the velocity of a wave is described by which of these options? Sound waves represent compressions and rarefactions of the medium, often generated by the surface of a speaker or your vocal cords. This image illustrates the relationship between density or pressure change and the waveform. The higher the pressure, the faster the speed of the waves. Conversely, the denser the medium, the slower the speed. The speed of sound depends on a numerical constant, whose value varies based on the medium. Let's review an exercise. A sinusoidal sound wave is described by a displacement equation. We need to find the amplitude, wavelength, speed, instantaneous displacement, and maximum speed of the oscillating element. To solve the exercise, we need the general expression for a wave. The rest of the solution involves simple substitution of the given values into the wave equation components. Consider this multiple-choice question. All mechanical waves require a source of disturbance, a medium, and a physical mechanism for particle force interaction. Which option is the correct answer? We move on to the Doppler effect, which can be observed with a passing train. You can explore this phenomenon further using the provided applet links. The general Doppler formula relates the frequency heard by the listener to the frequency emitted by the source. The positive direction is defined from the listener to the source, resulting in a higher observed frequency when they are moving toward each other. Another question to consider. The Doppler effect causes the sound from a source moving toward an observer to appear to have what characteristic? Here is an example. A police car with a siren and a passenger car are approaching each other, both moving at 27 meters per second. The siren frequency is 250 Hz. We would use the Doppler formula to calculate the observed frequency. Finally, we touch upon ultrasound, which involves high-frequency sound waves. A common application is in medical imaging, such as seeing a 10-week-old fetus. In water, the wavelength for a 3 Hz frequency is about 0.5 This slide provides a visual summary of the different wave types and related concepts we have covered, including damped simple harmonic motion, traveling waves, and intensity equations.